Thank you all for coming. It's the last slot of the last day, and everyone's probably ready to start heading for the airport. Yeah, my name is Eric Evans. I am a software engineer with the Wikimedia Foundation. Full disclosure, I am also a member of the Apache Cassandra PMC, and I've been involved with the project since, since about as long as it's been at Apache. Used to work on it full time. It used to be my job, but that is not the capacity that I'm speaking here today. Since I've been at the foundation, at least in terms of modern Cassandra, I've had the best opportunity to kind of dog food it, to have an actual application, an actual use case to develop against, and to be involved with cluster operations. And so it's been quite an eye-opener, to be honest. And there'll be no blind advocacy today. I'm just going to kind of wear my user hat and be honest and straightforward about things. So the Wikimedia Foundation, well, Wikimedia is a kind of umbrella, a global movement for which there are a number of constituent projects, all sort of in the domain of freely available, collaboratively edited knowledge. The foundation exists in support of that movement. And it is our vision for a world in which every single human can freely share in the sum of all knowledge. Every month, Wikimedia properties serve out more than 16 billion page views. The best well-known of the projects, Wikipedia, has more than 38 million articles all by itself in almost 300 languages. And just by itself, just Wikipedia alone, you've got the number 6th ranked website according to traffic. My understanding is if you take the page rankings of all the other Wikimedia properties and combine them, you have something like number 5, but Wikipedia alone is number 6. So what does it take to run a site of this size? It may come as a surprise to some, but the software that's sort of central to every one of those projects is MediaWiki, and MediaWiki is PHP. So it's a LAMP stack, Linux, Apache, MySQL, PHP, or MariaDB and HHVM if you prefer. But simple, right? Straightforward, like a blast from the past in 1999. Except for the most comprehensive architecture diagram I could come up with is this. And even I can tell this is really hand-wavy and high level and kind of glosses over all sorts of things, missing things. It's not my intention to explain that. I would be the wrong person to do it anyway. A MediaWiki is crazy extensible. I mean, there's really no limit to how you can modify its behavior, how you can extend it. And we run a lot of extensions. And that, and combined with the scale, makes things interesting. One of the things that makes things interesting is called Visual Editor. It's an add-on. And it forms the basis of the use case I'm presenting on today. So a wiki is basically an editable website. And websites serve HTML. And if we had to edit HTML markup, then this would be really painful. So we usually have some kind of relaxed syntax markup, something that mirrors the semantics that we're interested in, but that's easier to edit. So this means we need to convert from that format to HTML. And when we go back and edit, we edit the wiki text as it's called in MediaWiki, and then we save it, and then we re-render that to HTML. What Visual Editor provides is a WYSIWYG editor. What you see is what you get. So instead of mashing edit and getting a web form with a text area that you enter this wiki text in, I mean, you just stay on the HTML representation and you go to town. You can click anywhere in the page and just start editing, and there's format editor controls. This uses HTML5's content editable. So the web browser is technically the editor, and you are editing the HTML directly. But it kind of goes without saying that if we're going to do this, we need to be able to now convert in the other direction, because we have 15 years of document history in Wikitext. We have a sizable group of editors who have workflows based around Wikitext. It's a big ship. It would take a long time to steer, even if we did decide to just shift to HTML directly. And this makes things a little bit complicated. So The biggest complication is in performing diffs, right? We want to be able to do diffs between arbitrary revisions of the document and see only the normative changes, just what the editor changed. So we can't normalize any portion of the document outside of what was actually edited when converting from HTML. And the way we do this is by passing along all sorts of additional metadata. You know, as you're parsing the document from Wikitext to HTML, you kind of figure out, you know, at the time, what would it take to preserve this formatting and just pass along that information in the form of additional metadata. So in this really contrived example, when you see a link that's formatted with double brackets like this, in Wikitext, that is a wiki link. It's different than a normal link. It says that this document is not only on the same wiki, but in the same namespace. And so you want to maintain that distinction. So you can see here that we've passed along an RDFA attribute, rel, to indicate that, with a value that indicates this is a wiki link, so that we know how to put that back. And if the text of the link were the product of a template, then you want to execute this template and transclude the output into the HTML. But you wouldn't want to take that output then and put it back into the wiki text. That would just be wrong. So here we're wrapping it in a span with RDFA attributes to indicate that that's the product of a template. And then we have this data parsoid attribute, this private attribute that we pass along as well that can actually contain the contents of the template. And that private attribute, the data parsoid attribute, can get really verbose. It can get right down to like character and byte offsets if need be. So to this end, we have a stateless microservice that we call Parsoid. It's written in Node.js. Its purpose is to take a specific revision of wiki text and to convert it to an editable version, an editable representation of HTML. You know, all the metadata necessary that if edited and passed back to Parsoid, it can be converted into wiki text. And if you diffed that wiki text to the previous wiki text, you'd get just the normative changes. So not just document semantics, but also syntax as well. You might wonder, well, why not just have MediaWiki, parse HTML like this, rather than have an external microservice? And the answer is, it's kind of slow, it's computationally intensive. The output is larger, so it would take longer to transfer, which also drives up page load times. Even the DOM is more complex to the point where it actually takes the browser longer to work out. So for anybody who's not editing the HTML, this would actually be kind of a regression, and Visual Editor is an add-on. So that's one good reason to have it as an external service. The other is it lets us scale this out horizontally, independent of everything else. And the output, the responses from Parsoid are very cacheable. So we place these behind Restbase. Restbase is another service from Wikimedia. We use it kind of in place of service discovery. We use it to aggregate microservices. It sort of produces an API which is composable in the result of an arbitrary number of backend requests and responses and transformed. It's very flexible. And it also performs durable caching. We have pluggable backends for this, but we use Cassandra in production. So it looks something like this. Parsoid's not the only service that we aggregate behind Restbase. There are others. Usually it's kind of a similar theme. You have some sort of expensive transform, just to solve a particular use case. The response is cacheable, and we put that behind Restbase. Okay, so that's our use case for Cassandra. Let's dive into that a little bit. So in our environment, we have one cluster that spans 2 data centers. We're running Cassandra 226. We're using Cassandra's network topology strategy to distribute a total of 6 replicas, 3 to each data center. Within each data center, we have our hosts spread out across 3 rows. That's kind of the unit we're planning for failure is to lose at most a row. So we have the replicas distributed across those rows as well. We're using fairly beefy hosts, 16 core, 32 threads, 128 gigs of memory, SSDs. We're running a 54-node Cassandra cluster despite having 18 hosts, and I'll explain how that works a little bit later. Cassandra's default compression is LZ4. We're using deflate. We actually also see better compressed sizes, I think, than what most people do. I'll also expound on that a little bit as well. And it is a read-heavy workload, which you might expect since I described it as a durable cache. But at 5-to-1 ratio, maybe it's not quite as read-heavy as you might expect. The reasons for that are we also have a very robust CDN, and Restbase is typically only queried on a cache miss from the CDN, so the read requests are a bit lower than you might expect. And since we really don't know which documents, we don't know how to anticipate which documents might be edited with Visual Editor, we prime the cache on every single document edit. So the write rate is perhaps higher than what you might expect as well. Okay. Everything in Cassandra and everything else you might want to talk about kind of pertains to the data model. I mean, you have to get the data model right if you expect performance characteristics to be what you want them to be, and then that affects everything else. So I'll just start with the data model. We have this primitive, storage primitive in Restbase called key revision value. And the key and key revision value for the Parsoid use case is a combination of the site domain, the site name, and the document title, because documents are unique to a site. And in the Restbase's Cassandra storage module, that key ends up being the partition key in Cassandra, so that's what determines distribution throughout the cluster, ultimately. The revision and key revision value is the revision as supplied by MediaWiki. So this is a monotonically increasing integer value, comes right out of the MySQL database. Every time an editor matches save, a new ID is created. This maps to that ID. And obviously, you have more than one revision for a document, so this is a many-to-one relationship with the key. But then we have this value called a render, which is kind of a revision of the revision, or a version of the revision, keyed by a time UID, many-to-one relationship with that revision. And the reason for that is we're doing full-page renders, so there's always some material here that wasn't a part of the actual Wikitext document, the canonical document. Sidebar, footer, headers, or templates. If the document uses a template, you can imagine that template being changed somewhere, and every document that uses it now needs to be re-rendered to HTML. So the render, as shown here, is basically a point-in-time representation of the HTML for a given revision. And then the value is just a blob, so in our case, this is usually a string storing the HTML for Parsoid. Would look like this as CQL-DDL, or if visualized more directly, again, you have a key made up of the domain and the title, and then an arbitrary number of revisions, and then each revision has an arbitrary number of renders. And this is kind of how the data is laid out on disk. I mean, Cassandra does store in sorted order. Our data is going to be sorted first by the revision, then by the render, which is important when you're talking about compression. So compression is a topic that we have spent a fair amount of time on, and we'll probably spend some more still, because what we're storing is document history, and there's a lot of value in that. But space is finite, so the better use we can make of that space, the more history we can store, then the more use cases we might be able to enable. Sort of the hallmark of any general purpose compression algorithm, if you remember, we're using deflate, is the ability to look for repetition within a stream and then store back references to that. As it turns out, our revisions have very, very little changes typically between one and the next. And since they're stored sequentially, there's a lot of repetition there that could be found. Cassandra has this parameter called chunk length that basically determines from its stream, as it's reading or writing data, how much of that to pass off to the compressor. So we jack that wide open. 64 kilobytes is the default. A lot of people go down from there. We actually go up as high as 512K, in order to pick up more of that repetition. And it's because this works so well for us, that we have been looking for compression algorithms that don't have a fixed size window. Deflate has a fixed size window, I think it's 31K, from which that it can look for repetition within that stream. Some compression algorithms, LZMA, Brotli, for example, will let you specify the size of that window. Brotli is a really good compression algorithm all by itself. It's kind of made to be a better deflate than deflate. Apples to apples, it will produce smaller compressed sizes with lower computational cost. So it's pretty much a win no matter what, but it will also let you change that window size. And so larger window sizes and a larger chunks length still, we have a lot of potential to really to get some space savings here. I wanted to have more formal results for this, but my attentions got pulled elsewhere more recently. So I will have these slides posted. There's a link to the ticket where and the preliminary work is done. You can look at that if you're interested in that. Another topic that we have spent a fair amount of time on, and will probably continue to spend a fair amount of time on, is compaction. Cassandra has a log-structured storage system, and compaction is kind of the price you pay for having log-structured storage. It runs asynchronously in the background. The intention is to reorganize the data to make it more optimal for reads. At a very minimum, you want to reduce the number of files. You want to merge many files into fewer files. If possible, when doing that, you'd like to reorganize the data in such a way that the results will be near each other and can be read from fewer files on disk. This is also your opportunity to garbage collect any obsolete data. If you overwrite a value in a log structured storage, you're basically just placing a newer value in that masks the old one. And a delete is kind of a special case of that overwrite. You write a tombstone, which is a marker that says any previous values should be considered deleted. Compaction is your opportunity to expunge those. And then there's also TTLs, which is basically putting a timer on a value where you expect it to be considered deleted once that timer's up. So this is your opportunity as you're merging files together to drop what's no longer relevant. The other important function of compaction. When we first set this cluster up, there were only 2 compaction strategies that were available: size tiered and leveled. Size tiered just takes files of similar sizes, combines them to make fewer files. It's oblivious to your column distribution, but it doesn't use a lot of I/O. Then you have leveled, which is kind of clever. It's inspired by Google's LevelDB. You take files of fixed size, fairly small sized files of fixed size, and you arrange them in levels of non-overlapping ranges. And then each level has a sort of maximum number of files that are allowed for that level. And with each successive level, that number is exponentially larger. When a level has too many files, you merge some of that data into the next highest level. So a simple point query, if you're just looking up a single column value, the worst case for that is the number of levels in terms of tables that you need to read from, and that tends to be a very small number, so this is very optimal on reads. And we're serving up pages to clients with a web browser on the other end, and latency matters, and so we thought this is definitely for us. Turns out it's not, mostly because it's just way too much disk I/O, way too much compaction throughput. To make that algorithm work, you're compacting your data, and then you're compacting it again and over and over and over again. You're retreading all of that same data multiple times. It produces pretty much the most efficient reads, but it does it with pretty much the least efficient use of the disk. There's allocations on the heap as part of the compaction process. So even if you can manage the disk I/O, you're pushing throughput on the JVM's garbage collector. You're probably starting to see some pauses. It's just really hard to accept that much compaction throughput. But along came date-tiered compaction after the fact. And this really seemed like this would be our jam because it's clever. Instead of combining files of similar size, like the upper one, size-tiered, what it does is it uses its knowledge about the minimum and maximum timestamps in a file to combine them instead by their date and time, by when they were written. The idea being, if your data set is total ordered, and if you remember ours is, it's first by revision, then by time UID, newer values are always sort higher than previous values. If your data set is total ordered, then arranging things by date arranges your data in order because time and date are total ordered. And it can do this in pretty much the least amount of disk I/O. So this definitely seemed like the thing for us, except for it really wasn't. Without going into too deep of an explanation about how date-tiered works, I'll just say that it is so easy to defeat those optimizations that for all intents and purposes, they just don't work. Any kind of out-of-order write is enough to completely defeat those optimizations. A delete is an out-of-order write. An update is an out-of-order write. And read repair is an out-of-order write. And you kind of want, you kind of want your data, you kind of want read repair there to kind of counteract any inconsistencies that might build up over time. So it did not work out nearly as well as we'd hoped. It doesn't work as nearly as well on paper as it in real life as it does on paper. We're still using date tiered. We're still trying to figure out what the right thing to do is. With the optimizations defeated, you're pretty much kind of left with what size tiered does, so we may just switch to that. There's another out-of-tree compaction strategy called time window compaction strategy, which isn't sensitive to these out-of-order writes, and that may be our saving grace. But yeah, this is still kind of an outstanding problem. And it's actually worse than just the not really being optimized, well optimized for reads. If you remember, you also need to expunge obsoleted data, and compaction's your opportunity to do that. There's this problem called the overlapping tables problem. When compaction happens automatically, it's only ever working on a subset of all of the tables on disk. And so when it encounters a tombstone, it encounters any sort of droppable data, any data that's a candidate for not writing in the output. It has to take into consideration the picture of, like what exists in these other tables, the ones that's not compacting. If there's the potential for a value that precedes the value that you're considering dropping, then dropping it would, perhaps resurrect a value that was supposed to be deleted. You can't do that. So it takes a look at the indexing for, the metadata for these tables not being considered, and if these files don't contain the same partition key, well then we know it's safe and we can go ahead and drop the data. There's also a maximum purgeable timestamp, and so we can look at that and further optimize whether or not we can maybe rule out one of these tables. But if we just can't be absolutely sure that there isn't a preceding value, we have to keep it and make it part of the output of the compaction, and hope that a subsequent compaction of a subset of the tables will pick it up. In our case, if you remember, we're storing document history all tied to one partition key, which means that over time, our partition keys are pretty much across all of the tables. And with timestamps not really being ordered, those don't do much to help optimize things away. And so we have huge amounts of data that should be candidates to be dropped and never does. So this is another problem that we haven't yet have a solution for, and it's hurting us. Moving on, Cassandra is written in Java. It runs on the JVM. It's a database. We're concerned about latency, so of course, garbage collection is a thing. JVM garbage collection. This is actually a story with a fairly happy ending. When we ran concurrent mark sweep, back in the day, we spent an inordinate amount of time trying to get this right, trying to get GC right. Never really happy with the results. Always working on it, it felt like. Then we found G1 GC, and most people will describe G1 as being, mostly tuning free. Maybe you need to give it a bit more heap than what you're used to, give it some working space to work its magic. We found that to be mostly true. We had one exception to that. In G1 parlance, they call a humongous object one where it takes up more than half or more of your region size. So G1 divides your heap into some number of regions of some size. And if you attempt to allocate an object that's 1/2 that size or larger, then it puts it in what it marks as a humongous region, and it puts it in a special area, and it doesn't put more than one object per humongous region. It treats them in an exceptional manner. So if you have too many of them, then it can kind of destroy the collector's efficiency. In our case, it was calculating the 4 meg regions, and we had enough data, enough objects that were 2 megs or larger, that actually did create some inefficiencies. So the one setting we overrode was to increase the size of the regions, and that fixed all of our problems, and it's worked beautifully since. All right. Another subject that has taken up a great deal of our time is node density. you have a data set of some size, you have a throughput, how do you size your cluster? How many nodes do you put, do you install and of what size? Unfortunately, this is, a little bit more, there's a little bit more to this than what you'd like it to be. You'd kind of like it to just be based on the hardware capacity you have available to it, and then just, divide by your throughput or your size. But Cassandra just does not vertically scale to modern hardware nearly as well as you'd like it to. And some of the things that will cause you problems are, for example, compaction. Those algorithms are, applied to the data set that, of a single node. So the larger that data set is, if the efficacy of that compaction strategy is poor, then the worse the problem becomes, the more data you have under a single node. The more share of the data that a node has, then the higher its share of the throughput is as well, and that's more throughput on the GC, which could make tuning it more of a challenge. And bigger nodes also, you have the blast radius to consider. Like, what happens if it fails? And I need to bootstrap in a new node. It takes a lot longer to stream 10 terabytes than it does to stream 1, for example. So you find yourself, not able to fully utilize modern hardware, and you need a way of deploying, of basically scaling the node size down without wasting your hardware. What we do is we spin up multiple processes. I wish we were, something more sophisticated than that, but it's not. We use Puppet in our environment, so we have Puppet write out multiple configuration directories that reference multiple data directories, and we write out multiple systemd units, and we just spin them up. And to make matters worse, we have a RAID 0, a shared RAID 0 on the host, and all of the instances use the same RAID 0. So there goes your blast radius again. One disk fails, and the RAID, the array is gone, and all 3 instances go with it. And that's actually happened to us. So don't do that. It's not good. What I wish we'd have done instead is used, any one of the the standard, commonplace abstractions that people use for carving up hardware these days, virtualization, containers, or we could have just even bought blades. I think would have made sense, if you're worried about, the number of machines and the size of them, the data center occupancy issue, then, maybe blades would have been a good option. Multiple processes actually works. It works better than I kind of expected it to, but it was a lot of work to get it set up, and it's kind of different and weird, and it has, it's operationally, it's more complex. There are definitely better ways. Okay, so those are the kind of the things that, we focused most of our time on, and of course, you don't spend time working on things that are working well for you, so there's, I guess, a little bit of a negative leaning to most of that stuff. I'll kind of pull back a little bit and just, touch on what I think works and what doesn't, more broadly. So the good, basically everything that you hear talked about in Cassandra's, sort of core feature set, all of that stuff is awesome. Like the fault tolerance and availability you get, the way you can game, your replication factor to trade away, consistency for availability, all of that is fantastic, and it's well instrumented. There's good visibility. So if you like to monitor, if you're a monitoring nut like I am, it's really awesome because you can kind of get in and see what's going on with every aspect and every part of the system. It's ubiquitous at this point. A lot of people are using it, which helps. You go on Stack Overflow and you find answers to questions that you find out are a lot more common than you thought. There's software being written for it. It's got a big, robust community of friendly, helpful people. If you need to get a question answered, or you just want to have lunch with somebody and bounce ideas off of them, it's good to not be the only one or to be the early adopter. The bad, I would say number one for me is usability. And I know a lot of my fellow Cassandra developers would probably think that this is being unfair, and they would probably point out, rightfully so, that usability is way better than it was like a year ago, and way better still than it was 2 years ago. And they're right, it is. It's way better. And it's still horrible It's still awful. I would argue, I don't necessarily have like an idea of how you would fix this, but I think I would argue that just the fact that you have to deal with compaction at all, that you have to think about it. You have to know your data model and your access patterns, and then understand all of the available compaction algorithms in order to choose the right one and tune it appropriately. It requires that of the operator is kind of it doesn't make for a good usability story, I don't think. One of the things I think really damages usability is the fact that all of that nifty monitoring and management functionality comes via JMX. That's the kind of functionality you kind of want to be accessible to dynamic programming languages. Those are the people and the tools they use. JMX kind of puts that at arm's length from them. It kind of requires that you use Java, and then it's really unpleasant to do even from Java. This all sounds like I'm being very critical. I'm probably the one most responsible for the use of JMX if we went all the way back, but I truly think that was the wrong move. And then, like I've already pointed out, it just doesn't vertically scale as well as you would like it to, so you're left doing hacky things in order to take full advantage of your hardware. Beyond the bad, there's a few things that are very, very ugly, I think. The process of upgrading from one version to another is absolutely horrible. I just did one. I did one from 2.1.13 to 2.2.6. And that should have been a very simple, very straightforward move. It wasn't expected to be a lot of change between those two versions. In fact, 2.2.6 was released specifically because there were big, big changes coming, and it was like we didn't want to wait until all the way to 3.0. So it was kind of flushing out some of the simpler, more straightforward stuff. It should have been an easy move. And I waited till 2.2.6 so that other people would shake out all the nasty bugs. There were a lot of people running 2.2.6, a lot of people who've upgraded to 2.1, from the 2.1 series, and I tested it. I tested it, what I thought was very carefully. So you'd think there'd be no room for things to go wrong. Three critical things went wrong. And the new version had a new on-disk file format. And so the moment you start to upgrade, the compaction and new writes start to write the new format, and you can't go back because it's not backward compatible. You need this stuff to work really smoothly if your data format is changing like this. I know people, I don't know if I would go so far as to say you can't upgrade, but I do know people who do say that, who say that they would never consider an upgrade of a production system, Cassandra, that they would always set up a new cluster, double write, backfill, and then decommission the old one, which is really sad. These are smart people too. Like I said, I'm not sure I fully agree that it's impossible to upgrade. But I do see where they're coming from, and that's pretty sad. I think a lot of this boils down to quality control between releases, that the upgrades are so bad. And it was because of that the release process was changed to something that's kind of vaguely like Intel's TikTok, where an odd release means one thing and an even release means another. And the idea was to try to keep trunk more or less releasable to get new features out and get people to test them while maintaining a stable base. And this was done because what people used to do is they used to do like what I did. They waited till like the .6 of the miner, in the Semver release version. They waited till .6 when all of the really bad things had blown up and hurt other people before upgrading. And so this was like an idea of trying to solve that problem so everyone didn't just stand around waiting, like playing a game of chicken to see who would upgrade first. And all this change of the release process did is just obscure where that sweet spot is when it finally becomes stable. Like now nobody knows. It's like a way of tricking people into running the. And if you think that I'm being overly harsh there, just search the mailing list archives. The confusion about what version to run is just, it's pervasive. Like nobody knows what version to run. Everyone's very confused by it. It really did, you just made that worse. So. With that, I maybe have a couple minutes for questions, if anybody has them. Yeah? Do you run vNodes? We do run vNodes, yeah, 256 per. Yeah, that question's come up before. If we could start over, would you use a completely different database? I'd go back to the good. It's like, I don't really know what else would have, we're all guilty of bias, and I'm probably pretty heavily biased or whatever. So there's the temptation when you're sitting down to evaluate it, the problem and what you need to kind of, come up with a set of requirements that match what you know and what you're familiar with. So short of a bias like that, though, based on the requirements, I'm still not really sure what else you would use. I know we are kind of having, we do kind of have a close eye on ScyllaDB, which is a Cassandra compatible ish re-implementation in C++. They seem to be doing good things, so we're kind of keeping an eye on them because I think most of my complaints boil down to sort of a quality control kind of, like, the release process is, it's they either boil down to kind of, the release process, the quality control, and the testing, which is largely, Cassandra's very difficult to test because of its CEDA architecture and the use of singletons. Either boils down to that, or they boil down to issues related to the JVM, both of which, if you re-implement C++, kind of go away. So we're hopeful about that. Anything else? Going once, going twice. Okay, thank you.